Greetings everyone, this is example number 3 from the example problem handout. And so in this problem we have a 6 kilogram cement block sitting at rest on a scale. So we've got my 6 kilogram block here. And it says find the weight of the cement block. So we're looking for the gravitational force exerted by the nearby planet. And find the normal force exerted on the block by the scale. And so you can see that the block and the scale are scrunched up, squeezing together, and so as those surfaces press together, there's going to be that normal force. So I'm going to turn this object into a free body diagram. So we're going to draw the two forces that are acting here as this thing is at rest. When it's at rest, I know that the acceleration in the y direction is 0. It's not accelerating. There is no acceleration, so that's going to be very important for us in a second. So we have the force of gravity is going to be pulling vertically downward towards the center of the Earth, which will nearly always be vertically downward in every problem that we solve. And then we have the normal force, which is going to be perpendicular to the surface that is pressed up against. So what I can do then is I can go ahead and let's start by calculating the weight of the cement block. So the weight, or the force due to gravity, is going to be equal to the mass times the gravitational acceleration on Earth. And so our mass of 6 kilograms times our gravitational field acceleration of 9.8 meters per second squared. And we're going to get a final answer of 58.8 newtons. It's going to be the weight of the cement block. So once I have that, I need to find the normal force. And so if there's no acceleration and there's only two forces vertically, the book would say, well, the net force in the y direction is 0. And the net force in the y direction is equal to, and the reason why it's 0 is because the acceleration is 0. So in the vertical direction, all the forces are going to add up to 0, the vector sum of the forces, so that includes their direction. And so if I want to think about it this way, the net force in the y direction, we've got two forces. We've got the normal force and the force of gravity. And what I'm going to do is I'm going to throw a little negative sign on the force of gravity because it was in the negative direction. And so when I rewrite it, and that's all equal to 0, when I rewrite this equation, what I can do is I can just essentially say that the normal force is equal to the force of gravity. Okay, so in this problem, with all these little congruency marks, those two forces are going to be balanced in this problem. And so if they're balanced, normal force is equal to the force of gravity, then I know that the normal force is equal to 58.8 newtons. And this is true because my acceleration in that direction was 0. Now a little side note, okay, this equation and this relationship would not be true if the object were accelerating. Because if it were accelerating, the net force would no longer be 0. And then we would have to make a new equation that involved whatever that m times a was. And we'll get to those. All right, this has been example number 3, and I hope that this has been helpful.